In this video, we'll be looking at set theorem, where we will just look at some of the unique properties that sets have. So the first one that we're going to look at is the complement of the complement. Let's say if you have the complement of a complement, we're saying that the complement of a complement will be equal to A. How does this come about, or how is this true? Let's say you have a Venn diagram like this, or a universal set, and you have a set in there where we are calling it set A. If you take the complement of set A, which is a complement, you find that what you remain with if we are shading is this part. This part is what we're calling a complement, which is just basically all the elements that are not inside set A. So in our case, all the elements that are not inside set A are found on the outside. So if we call this, we say let A complement be equal to B. Okay, and we don't call this A complement anymore, we call it B. Then what would be the complement of B in this case if we said B complement? If B is what is on the outside, then B complement would be what is in here. You see? So B complement would be equal to A in this case. So if we bring back, we say bring back A complement to be equal to B, you find that where there is B we replace with A complement, what we'll get will be A complement is equal to A. So you understand where this is coming from. The complement of a complement is equal to that given set. So if the set is A, the complement of A complement is just A. So you can actually gun this, you can swatter this, but this is the explanation behind this property. Okay, what if you, let's look at this other theorem. If you have A union A, A union A is just equal to A. How do we arrive there? Let's have our set again. Okay, in this case, let me say we have we are having two sets inside the Venn diagram, but it's one and the same even if you just use one set. If we take the union of A and A, it means that we are taking the elements that are in A and the elements that are in A again. And if let's say the elements that are in A are 1, 2, 3, 4, and 5. So we'll say A is equal to 1, 2, 3, 4, 5. And we are taking union with A again, where we have A to be 1, 2, 3, 4, and 5. So we can say that A union A is equal to 1, 2, 3, 4, 5. Again, you start with the other A. 1, 2, 3, 4, 5. Okay, like this. But we know that under sets, we don't write we don't write like this. We don't repeat elements. If you mention an element once, you only write it once. So if one, you've already written one, you only write one once. So this is supposed to be written as one once. Two is being repeated twice, but we don't repeat under sets. We just write two once, you write three once, you write the four once, you write the five once, and you get this. But you find that this is just equal to A, like we've said. So A union A will just be equal to A. Okay, so that's one of the properties that you need to consider. The third one would be, what if you have A? What if you had A intersection A? A intersection A will also give you A. So I'm not going to show how we are getting there, but you can just swatter this. Okay, but you can test it using what we have, the method we did here, and you find that it will just give you A also. And the other one that we can look at is the commutativity of sets. So sets are commutative. So for example, addition is also commutative. If you have 5 plus 4, you can write it as 4 plus 5. So in terms of sets, if you have A union B, this is the same as B union A. Okay, or if you have A intersection B, this is the same as B intersection A. So this is the commutative property of sets. I think even multiplication is also commutative. Okay, but we are talking about sets. So in terms of sets, this is what we mean. This is what we mean. Okay. The other thing that we need to look at is number 4, which we are calling the associativity of sets. So let's say you have A union B, A union B in brackets union C. So it means that you are taking the union of A and B first, then you take the union of what you get. So if the union of A and B is, let's say, set X, then you get set X, you get it with union with C. That's what we mean. But this can be also written as A union B union C, where you have B union C in brackets. So these are the same no matter where the brackets are, they are the same. So you can take the union of A and B first, then you do it with the union of C, or you can take the union of B and C first, then you do the union of A. So if we had, for example, we were saying that A union B is equal to set X, and the B union C is equal to set Y, we can say that X union C is the same as A union Y. Okay, that's what we mean by associativity. But some things are not associative, but for sets, we are saying that sets are associative. So we can also say that A intersection B intersection C, where you have these two in brackets, is the same as A intersection B, where you have these two in brackets intersection C. So you can start off by finding the intersection of B and C, then you find the intersection of what you get here with A. Or you can start with the intersection of A and B, then you find you take the intersection of what you get here with C. So there's actually an example you can use for this, where you can write up a set. For example, if I'm not going to do an example, the video will go, yeah, is going to be long, but if you want an example, just make a comment in the comment section, then I'll be able to help you. Okay, so the other property that we're going to look at is the distributive. The distributivity of sets. So sets can be distributed. What do we mean by this? If we have A intersection in brackets B union C, this can be distributed. You can distribute this to this and also to this, and what you get will be A intersection B in brackets, and this symbol will come back at the middle, and you have A intersection C. Okay, that's what you're going to have. And if you had A union and open bracket B intersection C, you can distribute this to each of the sets, and what you are going to get once you distribute will be A union B in brackets, and you bring back the symbol which was in the brackets at the middle, so it will be here. You put an intersection and open brackets A union C. That's what we mean when we say that sets are distributive. So you can also factor out this. When you factor out this, you will come back to this. You will have this. Okay. Okay, so we move on. Number 6, you have A intersection with an empty set. So when you intersect A with an empty set, what you are going to get will be an empty set. We know what an empty set is. An empty set is just basically a set that does not have anything. Okay. So if, for example, you have set A to have 1 and 2 as its elements, and you are intersecting set A with an empty set, what you will get is an empty set. But how do we get this? So you realize that A has subsets, and the subsets of A in this case will be a set that will just have 1, and you have a set that will just have 2, and you have a set that will have a set that will be just empty. So each set, one of the properties about sets is that sets always have an empty set inside them. So any set has an empty set inside them. So if you decide to, if you write A like this and you write your empty set like this, where you say an empty set is just empty, you will realize that the only common thing between A and the empty set is this, the emptiness. Okay. Hence, A and the empty set only interact, the only intercept, the only intersection they have is the empty set. Okay, so an empty is a subset of every set. Take note of that. An empty set is a subset of other sets. So inside every set there is an empty set. So when you intersect an empty set with any other set, the answer is going to be the empty set. Okay, so that's the, we can say, the sixth theorem. Okay, so what's the next thing? The union. The union of the empty set with another set. So the union of the empty set with any set is just that set. So in our case, we are considering if you try to take union of the empty set with set A or any set, you will find that the set you have will be just that set. Okay, I think that's not hard to understand. That's not hard to understand. Okay, so what other things can we look at? Okay, we can also look at when you have when you have the intersection of a set with the universal set. So the intersection of any set with the universal set is just that set. So the intersection of set A with the universal set is set A. Okay, why do we say this? If this is your universal set U and you have a set inside which you are calling set A, you realize to say that this entire part, including set A, is the universal set. And let's say if the universal set had 1, 2, 3, and 4. So you'd say that the universal set, you can write it as 1, 2, 3, 4. And set A, for set A, you find that you only have one element in set A, which is 4. And you say A intersection U, universal set. Where are these intersecting? You find that they are only intersecting on the 4. Okay, so you can write that A intersection U is just 4. But 4 is also equal to A. 4 is also equal to A. So that's where this conclusion is coming from. But what if we add A union the universal set? So I'm not going to represent the universal set by U. This is confusion. We'll use E. E also represents the universal set. If you don't use U, you can use E. It wouldn't have made sense if I said A union universal set. These look the same. So that's why we're using E. Okay. So if you take any set and you find the union of that set with the universal set, what you get is the universal set always. So let's say if you have set A, in our case set A just has one element which is 4, and we have the universal set which has 1, 2, 3, and 4. The union of these two will be, you get all the elements that are in here, you also get all the elements that are in here. So we can say A union E is equal to 1, 2, 3, 4, 4. But we don't repeat under set theorem. You don't repeat what? You don't repeat an element. So we are not going to put 2 4s just because 1 4 is coming from set A and the other from E. No, you don't write like this. So your answer is just going to be like this. And you realize to say that this is just equal to the universal set. That's why we have this this property. Okay, so what other properties can we look at? Okay, can also look at the property that says if you have A union A complement, you are going to get the universal set. Okay, so what do we mean by this? Let's say this is your Venn diagram and you have 1, 2, you have your set A to have 3 and 4. This is your universal set. Okay, if you were taught A to write set A, you would write it like this: 3, 4. A complement would be 1, the things that are not in A, the elements that are not in A is A complement, so it would be 1, 2. So if you take union of A and A complement, you find that what you have is 3, 4, 1, 2. And you quickly realize that this is just equal to the entire what? The entire Venn diagram or the universal set. Because if you look at this, if you were taught to okay, let me write it. Though I mentioned that sets have no specific order, but if you were taught to list the elements in the universal set, you would also list them like this, and you realize that these are just the same. Okay, so A union A complement is just equal to A. So even if you had B union B complement, you just have this will just be equal to the universal set. Okay, even if you had C union C or C union C complement, this will just be equal to universal set. And what if you had A intersection A complement? This would be equal to the empty set. So I'm not going to tell you how this comes about, but this will be your homework to find out why A intersection A complement gives you an empty set, and also find out this why the complement of the universal set will be an empty set. Okay. Okay, what other properties can we look at? Okay, I think that these are enough. So we can try to do a question or two based on some of these theorems that we have that we have used here, but you will find that they will not directly give you this, or they won't directly say that they give you this and they ask you what is this equal to, and then you just do this at wasanga. No, you find that this will just come along as you are solving a question, then you reach this point and you can simplify from there to this. Okay, so we're going to meet in one example or two that are based on this theorem.